All right. This section 4.3 is, in my opinion, one of the most important sections out there. So this section extremely important. Okay, not just for this class, but for calculus, for all of the future math. Okay, it turns out when you take future classes, you're going to be seeing this word a lot. Logarithmic function, logs. Okay, so a log is pretty much the inverse of what we've been doing. So in 4.2, we were dealing with a to the x, and here in 4.3, we're going to be dealing with log base a to the x. It turns out that that's not a coincidence. These two functions are inverses. Okay? Why do we care about that? Let me go back over here. I'm trying to give you motivation for why we need this chapter. So in math, whenever you have addition, oh, forgot how zoomed in my usual pages. So if we have addition, don't know why the screen's like that. Is it 2? There we go. I'll just say add because I can't spell. So whenever you add, okay, you cancel it out with subtraction. These two are what we call inverse operations. They cancel each other out. Same thing with multiplication and divide. These two are inverse operations. All right? When you square something and square root, I mean, there's a technicality here, but I'm not going to go into that. Those are also called inverse operations. They undo each other. So, for instance, if you had plus 5, you would undo it with a minus 5. If you had times 3, you would get rid of it with a divide by 3. If you had x squared, you would get rid of it with a square root. More than that, not only that, you can raise to the n. And the nth root. These are inverse operations. So in this case, x to the n and the nth root, they cancel each other out. Now, when we have an exponential, and a log, it turns out that these two things cancel each other out. These are also what we call inverse operations. Okay? If you have 2 to the x, then 2 to the, if you turn the exponent into a log, they cancel each other out. If you have a log, and on the inside, if you put 2 to the x, they cancel each other out. We'll go more into that later. But basically, if you add something, how do you get rid of it? You subtract. If you're multiplying, how do you get rid of it? Divide. If you're squaring, how do you get rid of it? Square root. If you raise something to the nth power, how do you get rid of it? The nth root. Well, it turns out if you have an exponential, how do you get rid of it? You log it. If you have a log, how do you get rid of it? You make it an exponential. So those are how you cancel each other out. It's a hugely important topic in this section. And just all of math, really. But anyway, going back to the handout, it says y equals a logarithmic function is defined by this. Now this letter here in the middle isn't a typo. That stands for if and only if. And whenever you see if and only if, it's just math people don't like to say the same thing twice. So it just means that this whole process works both ways. So whenever something works both ways, they say if and only if. Okay, these are two forms. You have your logarithmic form and your exponential form. And going between the two is known as converting. And that's going to be what we're going to spend a lot of time working on today. Okay, so going back here, if I'm dealing with a log, so logarithmic form, whenever we're dealing with a log, you have your answer. Or you know what? It doesn't really matter. Usually when you see answer, you think of it as at the end. So let me go ahead and write it that way. So for logarithmic form, you have log, the base goes on the bottom. It's a subscript. We have the inside, and then it's equal to the answer. Okay? Log of a base, it's the same base as the last section. It has to be positive, it can't be 0 or 1. Of the inside equals the answer, and then we have the exponential form. All right? And now for an exponential form, the base is bigger. The inside is the exponent, and the answer is the answer. Okay, so look at the difference between the two. For a log, there's literally the word log. We have a subscript. And then we have the inside, which is going to be in parentheses. If it's just one thing, they tend to get lazy and don't put the parentheses. But if you have more than one thing, you need to put a parentheses around it. Equals the answer. The other form is base raised to the inside equals the answer. Now remember, for an exponential, the inside is the exponent. All right. So one thing we're going to have to do in this section is we have to convert from one form to the other. So what we're going to do is we need to know how to go backwards and forwards between these two forms. Okay? And there's two steps, and I have it on your handout too, but here I have more room. So the steps to convert. The first thing you're going to do is, first the base stays the same. Let me say switch forms first. So we're going to switch forms. If you were in log, you're going to be in exponential. If you're in exponential, you're going to be in log. But here's the rules. Base stays the same. That doesn't change. The only thing that changes is for logs, the base is the subscript. For exponentials, the base is the big number that you raise to something. Okay, the base stays the same. And then you swap the inside and the answer. So inside becomes the answer. And the answer becomes the inside. You know what? That's actually going both ways. Sorry. Oh no, that's right. Inside becomes answer, answer goes on the inside. So what I mean by that is if I'm going to make something up. let's say log base 2 of 8 equals 3. So this is actually a true statement. Our brain doesn't really understand this, though. Our brains don't work in logs. For instance, in addition and subtraction, our brains like addition better. For multiplication and division, our brains like multiplication better. For squaring and square rooting, our brains like squaring better. It turns out for exponents and logs, our brains prefer exponential. Okay? So logs are just kind of foreign. So what we do is we convert them to something that we can actually understand. So what's going on here is we switch forms. So this is log. So I'm going to change it to exponential. The base stays the same. So the base was a 2. That stays a 2. But the inside becomes the answer. The answer becomes the inside. I notice that's a true statement. 2 cubed equals 8. So that's what we mean by converting. You want to get this guy, and you want to change it to be that guy. Or you want to get this guy and change it to be that. And all you do is these three things. You switch forms, the base stays the same, the inside becomes the answer, and the answer becomes the inside. So if we go to our handout, I have it written out, same thing I just said. Notice that the base stays the same. Okay. The inside is going to become the answer. The answer is going to become the inside. So this is called converting. And this is really huge to solving equations. So this idea here, going between these two forms, is the main topic for this lecture. Anyway, so let's do some examples. Oh, more stuff. So again, the inside becomes the answer. The answer becomes the inside. Same thing over here. The inside becomes the answer. The answer becomes the inside. Sorry, the answer goes to the inside. All right. Cool. So we swap the inside and the answer. Swap places. Well, first you have to change forms. And then the inside and the answer swap places. So let's look at this example. Okay. We're going to convert each of these to their other form. And on the homework, you have a bunch of these, and they want you to don't simplify them. Because they're all going to be true. 2 to the 5th is 32. I know that. But I want to write this as a log. So first, let's look at the base. Or sorry, I've been using different colors. We look at the base. The base is a 2. The inside is a 5. And the answer is 32. So if I'm going to turn it into a log, first we switch forms. When you switch forms, the form for a log looks like this. All right. The base stays the same. So the base was a 2. This stays a 2. Didn't really give myself enough room to write it. The inside, which is the exponent, becomes the answer. So this becomes a 5 as an answer, whereas the answer goes on the inside. There you go. Log base 2, and we read this by saying it this way. I forgot to say how to read it. log base 2 of 32 equals 5. Okay? Same thing here. Notice I'm trying to be a little shifty with how I write it. I kind of switched the order. But here the base is 5. The exponent is 3. The answer is 125. So if you wanted to switch forms, this would be log base 5. The base stays the same. And then the inside and the answer swap places. So the inside is 3. For exponentials, the exponent is the inside. The inside is 3, so it becomes my answer. The answer is 125, so it becomes the inside. Log base 5 of 125 equals 3. Now this skill of going from one form to the other needs to be quick. This idea should take seconds. Really quick. Just like your parents had you memorize your multiplication tables and your addition tables and stuff, same thing with these conversions. Going between one form to the other should be just as quick as you writing it out. And right now it's a foreign idea, but it takes a lot of practice. What I'm going to try to do is I'm going to try to come up with extra examples to work out, and you'll post them to Canvas. And if you work them out, I'm going to give you extra points on the homework, because the homework itself doesn't do enough justice for practicing these. You need to practice these completely on your own and more of like a speed challenge. You want to probably do 30 of them in, I don't know, 2 minutes or so. Anyway, same thing here. Log base 5 of 625 equals 4. So here, notice that this is written in logarithmic form. So here the base is 5. The inside is 625, whereas the answer is 4. So I want to switch to the other form. Now the other form looks like this. Okay? The base is the big number for the exponential form. So this is going to be a big 5. The answer goes on the inside, and the inside becomes the answer. And notice this is a true statement. 5 to the 4th is 625. Our brains like exponential. We don't like log. 1/2 equals log base 16 of 4. Same thing. 16 is my base. I want to raise it to the answer. The answer becomes the inside. And the inside becomes the answer. And notice this is another true statement. 16 to the 1/2 is 4. The square root of 16 is 4. All right, so give the 4 on the right a try. I'm going to make a video, post it to Canvas below this to show them worked out. But these are pretty much the same thing. I just want to make sure that you know what you're doing, that you're doing it right. Get some practice on your own. Okay, computing logs without a calculator. So if I go back to this blank sheet of paper, and if we're converting, I use green for the inside. Okay, let me put that. So let's say you have a log, and you want to figure out what the answer is. Well, again, our brains don't really work in terms of logs. Our brains work in terms of exponentials. So whenever someone reads a log, they don't actually do the log in their head. What they do is they convert it to an exponential in their brain. So let's say that the answer here is a question mark. And what you do instead is you convert this. So the base is still the base. The exponent the answer becomes the exponent, and the inside becomes the answer. Okay? So whenever we look at logs, we don't like them. So instead what we do is we convert, and this one makes your brain happy. Oh. Okay, but now let's look at this statement, this thing right here. If I were to put that into words, this says base to what power equals the inside. So whenever we're doing a log mentally, this is the question that we have to ask ourselves. Base to what power equals the inside? That is converting it. So whenever you read a log, this is how your brain has to read it. Base to what power equals the inside? So for instance, I'm going to start with an easy one. Log base 10 of 100, and we don't need our calculator. We look at this and we ask ourselves the question. So you see this, you ask yourself, ten to what power equals 100? 10 to what power equals 100? Well, that has a happy answer. That's 2. So therefore, log base 10 of 100 equals 2. And again, this actually does work out. You could type in log of 100 and you get 2 as an answer. Okay, so that's what we mean when they say could do logs without a calculator. They want you to ask this question in your head and see what the answer is. So going back over here, let's see. Notice I put a lot of them, but that's because these should be solved relatively quickly. So whenever we see this log base 2 of 4, we say 2 to the what is 4. What's your answer to that? Well, the answer is 2. Going to this one. 2 to the what is 16. 2 to the 4 is 16. Sorry. Someone's texting me something real quick. Grr. Okay. Sorry about that. Here. I'll go to these later. These get a little tougher. What about over here? 3 to the what is 3? Well, 1. 3 to the what is 27? 3. 3 cubed is 27. 5 to the what is 125? 3. Normally, if there wasn't, quarantine, this exam would have a calculator section and a no calculator section. And the no calculator section would be these problems, because you do not need a calculator to be able to do these. 5 to the what is 1/5? Well, that's a little tricky, but remember, we were dealing with this rule earlier. A to the negative 1 is 1 over A. Well, that's the same thing over here. This means the answer is negative 1. So the answer to logs can be negative, right? So these ones on the right side are a little harder. 2 to the what equals 1/8. Well, 2 times 2 times 2 is 8. So it's actually 2 to the negative 3. Because 2 cubed is 8, but notice that the 8's in the denominator, so that means it's negative. When you have the number in the denominator, it's a negative exponent. 3 to the what is 1/9? Again, 3 squared is 9, but since the 9's in the denominator, it's a negative 2. 5 to the what is 1? Well, anything raised to the 0 is 1. Okay? So doing these mental logs hopefully isn't too bad. I'm trying to de-scarify it. Sometimes you'll get some that are nasty, like this one. 8 to the what is 4. But if you ever run into that, you can actually make it into its own little problem. I know 8 is 2 cubed. I know 4 is 2 squared. And so notice we end up with our own little problem here. And so I wouldn't do these if I was making you do a no calculator portion, but these are some of the other more complicated answers that could happen. Okay. 9 to the what is 243? Let's try to figure it out. 9 cubed? Nope, way too much. 9 squared is 81. What about 9 to the 3/2? Okay, what about 9 to the 5/2? Sorry, I went backwards there. 243. Yeah, so the answer here is 5/2. 9 to the what equals 243? 5/2. 16 to the what equals 2? I think this is the fourth root. 1 divided by 4. Yeah. Sorry. All right. So most of the problems in this section, when you see the homework and they say do it without a calculator, this is what they mean. You can use your pencil, but they want you to do this mental converting. Base to the what equals the answer. Base to the what equals the answer. All right. So let's go to the next page. So it turns out that there's two really popular logs in math, two popular bases. The first base is base E. Remember how we talked about E last time? E was equal to the limit as n goes to infinity of 1 plus 1 over n raised to the n. Okay? But anyway, so base E, whenever we do log base E, it happens so often in math that we abbreviate it and we write this instead. Okay? Base E is what's called the natural base. All right? So log base E is written as ln of x. That's an L, by the way, not an I. Okay? The common base, now our whole number system is based off base 10. We have 10 fingers, 10 toes. And so whenever we're trying to do log base 10, we write log of x. So there's only two cases where you don't have a base. Okay? and that is log of x, in which case the implied base is 10. And then the other one is ln of x, where the implied base is e. And that's it. Those are the only two cases. So let's see if we can figure out these without a calculator. Remember, ln of e, the implied base is e. So e to the what equals e? Well, the answer there is 1. E to the what equals e cubed? 3. Remember, the base is e. The implied base is e. E to the what equals 1 over e? Negative 1. E to the what equals 1 over e cubed? Negative 3. The implied base of this one is a 10. 10 to the what equals 100? 2. 10 to the what equals 100,000? 5. Okay. 10 to the what equals 0.1? Well, 0.1 is just 1/10. So that's negative 1. Log, so 10 to the what equals 0.0001? Well, if you look at place value, this is the tens place, tenths place, hundredths, thousandths, 10,000ths place. And so this means that this is really 10 to the what equals 1 over 10,000. Notice that has 4 zeros, so the answer here is negative 4. Right? But anyway, in math, whenever you see a ln of x, the base is e. Whenever you see just a log of x, the base is 10. Any other time, they have to tell you what the base is. These are the only two implied bases. All right, so now we're going to do some basic log properties and then go into what the graph of a log looks like and do some graphs. Let me pause the video real quick so I can get something to drink. Alrighty, I am back. So, there's a lot of stuff covered in this section, so a quick recap. Logs, you need to know how to switch forms. So any exponential can be converted to a log. Any log can be converted to an exponential. All you got to do is keep the base, switch forms, but keep the base the same. And then the inside and answer are going to swap places. Okay? Now, whenever you want to do a log mentally in your head, ask yourself base to what power equals the inside. Whatever the answer to that is the answer to the log. And then the natural log and common log are two special logs where you don't need to write the base. If you just see a log by itself, then it's 10. If you see natural log, the base is automatically e. So anyway, let's do some basic log properties. All right. So everyone's aware that a to the 1 equals a. All right. Now, if I view this, let me write it in black so I can use the colors that I've been using for this lecture. A to the 1 equals a. Well, here's my base. Here's my inside. Oop. And here's my answer. So I can write this as a log. Log base a. The answer goes on the inside of a equals 1. Log base a of a equals 1. That's just a generic rule. I'm going to highlight over these in black now. The other rule that we all know is that a to the 0 is 1. So here's my base, here's my exponent, here's my answer. So if I convert this to a log, it's log base a. The answer goes on the inside of 1 equals, and the answer is 0. So this means that whenever you have 1 inside a log, the answer is going to be 0. If you have log base, if the inside is the same as the base, the answer is 1. If the inside is 1, the answer is 0. And these are just some basic logs that you do encounter a lot, and you should know. So again, this one, if the inside of a log is 1, the answer is 0. Just right off the bat. Okay? What this one tells me is if the inside is the same as the base, the answer is 1. That's it. So inside same as the base, the answer is 1. If the inside is 1, the answer is 0. Now, inverse log properties takes from the fact that a log base a with an a to the x in it is equal to x, and here a raised to the log base a of x is equal to x. So all these mean are exponents and logs cancel each other out. They're inverses. Remember, inverses, f of f inverse of x was equal to x. They killed each other. So a log of an exponential or an exponential of a log cancel each other out. So let's do some of these examples. These just take into account the properties. So this one, log base 3 of 3 to the 10. Well, a log and an exponential cancel each other out. So this cancels out with the 3 to the 10, and all I'm left with is 10. The one below it, the inside is the same as the log, as the base, so my answer is 1. Here I have an exponential raised to a log. And the bases are the same. The bases have to be the same for them to cancel. But the bases are the same. And so they cancel each other out. And all that's left is the 18. The inside is 1. The answer is 0. Okay, going over here. I have ln. Remember, the base is e. So ln and the log of an exponential cancel each other out, and you're left with the inside. The inside is 1. The answer is automatically 0. The implied base here is 10. The bases are the same. The base is the same as the inside. The answer is 1. 10 raised to log base 10. They cancel each other out, and you have 47 as your answer. Okay, so notice that I got the answers real quick just by applying these 4 properties. I know it's a lot to take in right now, but they're properties that you need to kind of get used to dealing with. You see these a lot when you get to calculus. All right, anyway, the rest of the section, basically the next 2 pages, focuses on the graph of a log. So now we're shifting gears, and we're going to the graph, and I have to pause yet again. The good thing about making a video early is that I can actually have time to myself. The bad thing is I get interrupted a lot. All right. So on to the graph. So when we're graphing a log, very similar. Remember that this log is the inverse of a to the x, and we're going to get into that in a bit. So the graph is smooth and continuous. Meaning you can trace it without picking up your pencil. Now, the domain and the range swap places. When we were dealing with a to the x, we had the domain and the range. So the domain was negative infinity to infinity, whereas the range was 0 to infinity. But remember that the log is the inverse. So what's going to happen is these two things are going to swap places. The domain is going to become the range. The range is going to become the domain. So the domain of a log is 0 to infinity, not including 0. The range is negative infinity to infinity. X-intercepts, since they're inverses, remember that this always went through the point there's a point right there, sorry. But it always went through the point 0, 1, which means that this will always go through the point 1, 0. So it has an x-intercept, but there are no y-intercepts. Asymptote. If the exponential had a horizontal asymptote, the inverse will have a vertical asymptote. So it has a vertical asymptote at x equals 0, a horizontal asymptote, none. And the behavior of the graph, I couldn't find a really good enough picture, but I'll do my best. So here, this is base is greater than 1. And notice that the bigger the base is, the flatter it gets. So base 2, we kind of have this shape. Base E, base 10, it starts to kind of flatten out. Now, if the base is between 0 and 1, remember the base can't be negative. Then the graph will look like this. I'll try to make my pictures. Okay, so let's say this is log base 1/2. The other one was green. Now, you know what? I won't try to. I'll show you the graph. So the closer it gets to 0, again, the flatter it gets. Let me show you on Desmos. I won't try to make a terrible graph. But notice that it's increasing if the base is greater than 1, and it's decreasing if the base is between 0 and 1. All right. So if I go to Desmos, I can graph this log base A of x, make a slider for A. Let's say A has to be between 0 and 2. Let me switch this. I was doing a video for a trig class earlier, so that's why everything's in pi. Okay. So notice that as soon as my base gets bigger than 1, I have a graph of a log. Usually this is the picture that comes to mind when I see a log. A graph that it has a vertical asymptote, and it kind of grows upward to the side. The steeper it is, the bigger the base, the steeper it gets. But if I'm below 1, Notice that the closer to 0 it gets, the flatter it gets. Okay, so this is the base increasing if the base is greater than 1, decreasing if the base is between 0 and 1. And just again to show you the interplay between log and a to the x, remember we were dealing with inverses last week. And so here we go. Let me change the colors up. Yeah, we have the log is red, the exponential is blue, and I can hit play. And you can see that the log and the exponential are inverses. Yay! Isn't that pretty? Okay, so they're inverses if the base is bigger than 1. If the base is smaller than 1, they're still inverses. All right, anyway, let's go into graphing. So again, whenever we see logs, our brains do not by any means like this. So here's my brain thinking. Here's the little thinking cloud. No me gusta. Right? So our brain doesn't like logs. So what we do instead is we find the exponential. We find this first. And since they're inverses, all we got to do is swap. And that's the easiest way to graph logs. Okay? Don't actually type in log of 1, log of 2, log of 3, log of 4. What you do instead is find the easier numbers and then work your way. So for instance, if I have 1/2 to the x, 1/2 to the 0 is 1, 1/2 to the 1 is a half, a fourth, 1/8, 1/2 to the negative 1, 2, 4, 8. Now to graph log base half, all I do is swap the values. So instead of -3, 8, I have 8, -3, 4, -2, 2, -1, 1, 0, 1/2, 1, 1/4, 2, 1/8, 3. So let's plot these points. 8 would help if I actually gave you enough room, right? Let's say 8's over here, -3. So I have a point right there. 4, -2. Oh. 2, -1. 1, 0. 1/2, 1. 1/4, 2. 1/8, 3. And you can see when I make my graph, here's my vertical asymptote. It kind of creates itself. And there you go. There's my log. Oh. And the way I drew it, I kind of make it look like it's hooking. It doesn't. It actually blends in with the axis. It gets so close to the axis that you can't tell, just like the exponentials did with the horizontal asymptote. All right, there you go. That's my graph. So whenever you see a log, graph the exponential first, flip the values, and that's how you create your graph. So let's go to the next page. What they're going to do here, and when I gave this speech, it was already, November time, hence Gilbert's pumpkin spice means. But anyway, they're going to get the log and they're going to move it up, down, left, right. Notice here we have the inside. This inside is my left, right. So if h is positive, remember it does the opposite. The graph moves to the left. If h is negative, the graph moves to the right. Okay. Here the plus or minus k is on the outside. So here if k is positive, the graph moves up. If k is negative, the graph moves down. Okay. So I put these because these moves are very basic transformations. And, I am not of your generation, so the best I can do is dad level jokes. So I try to do jokes for basic. Anyway, so graph this equation. And again, no me gusta. So we notice that this is base 2. So what I do is I graph the exponential for base 2 instead. I know it seems like, oh my god, I'm making 3 separate boxes, but this makes it so much easier, okay, whenever you're graphing transformations. So I have 2 to the x. I'm going to do a -3, -2, -1, 0, 1, 2, 3. 2 to the x is 1, 2, 4, 8, 1/2, 1/4, 1/8. And all I do to go from 2 to the x to log 2 to the x is I swap the values. So 1/8, -3, 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, 8, 3. And now I can do my transformations. Notice that this wants me to go left 4, down 3. So I'm going to go left 4, down 3. Now you can use your calculator if you want. I'm not going to force you to write it in terms of fractions. So 1/8 minus 4, -3.875. 1/4 minus 4, -3.75. 1/2 minus 4, and you probably know these answers off your head. I'm just kind of working them out. And then we get to the easier ones. 1 minus 4, 2 minus 4, 4 minus 4, 8 minus 4. And then down 3. So now I'm going to go get all these values, and I'm going to go down 3. -3 minus 3, so -6, -2 minus 3, -5, -4, -3, -2, -1, and 0. So these are the points that I'm going to plot. Okay, so plotting the points, I have -3.875, -6, -3.75, -5. Notice you can't really tell the difference. -3.5, -4, getting better. -3, -3, -3, -2, -2, 0, -1, 4, 0. And looking at this, I can see what my graph's going to look like. I can also tell where the asymptote is. Looking at it, I can see that I have an asymptote at x equals -4. So this is my vertical asymptote. Now, my default one, this has a horizontal asymptote at y equals 0. But since we swapped, this changes to a vertical asymptote at x equals 0. And since I went left 4, I go left 4, now it's x equals -4. But yeah, So that's how you were supposed to tackle these problems. If I give you this question on an exam, on the sheet that has that I have you scan and churn in, I'm going to have this for you so you can fill in the tables to work it out. All right. I also forgot on the previous problem to write the asymptotes. Bad, Gilbert. So here the asymptote was x equals 0 because this was y equals 0 for a horizontal asymptote. Therefore, it switches to a vertical asymptote at x equals 0. All right, almost done. We got domain and then some word problems, and then we are out of here. So, before I start, people keep texting me. All right, the domain of a log. If you look at the previous problem, everything to the right of -4 exists, but nothing exists to the left of -4. If I look at the graph over here, nothing exists to the left of 0. So whenever you're dealing with a domain, by default, you have the log base A of the inside. Let me use a darker color. Okay? And the domain is all values such that the inside is greater than 0. Okay? And this ends up becoming its own mini problem. You have to memorize this. If you're looking for a domain, remember this is the domain of a log. The inside of a log has to be greater than 0. Now earlier in exam 1, remember we had the denominator cannot be 0. We have the inside of an even root. Has to be greater than or equal to 0. And now we're adding a third rule. The inside of a log has to be greater than 0. Notice that each of these has their own unique sign. This rule has the do not equal sign. This rule has the greater than or equal sign. And in exam 1, those are the only two rules we focused on. That one and that one. But now, in this exam, we're adding a third rule, and it's the greater than sign. The inside of a log has to be greater than 0. So let's do some examples. Okay, so for this problem, looking at a graph will not count as credit. Just sorry to burst your bubble there. No credit at all. You have to do this by hand. So find the domain of the following logs by hand. Well, all you got to do is that rule. Inside of a log has to be greater than 0. 3x minus 5 has to be greater than 0. So x has to be greater than 5/3. If you're looking on a number line, you don't have to do the number line. But if it helps you out, go for it. 5/3, we have an open circle going to the right. And so my domain is parentheses 5/3 to infinity. That's it. That's all you got to do. So a generic log like this is pretty easy. Just the inside greater than 0, you solve it, and you're done. On this example over here, I try to get more creative and try to scare you into this crazy long thing. But again, this isn't that bad. We use the same rule. Inside of a log greater than 0. 5 minus 2x is greater than 0. negative 5. When you divide by a negative, the sign flips. So x is less than 5 halves. And so this is the same idea. Here's 5 halves. And we're looking for values that are less than but not equal to. And so here the domain is negative infinity to 5 halves. There you go. Okay? So remember, we're not finding x-intercepts. We're not setting the entire thing equal to 0. We're just doing the inside. The inside of a log greater than 0, and we're solving that. All right, so my TV froze, so I'm wondering, did my internet connection freeze? Hope not. All right, now the last one is a special case. And this says log base pi of x squared minus 16, and they want to find the domain. So we do the same thing. Inside of log greater than 0. But notice this is x squared minus 16 is greater than 0. Okay. Can you all think of what x squared minus 16 looks like? It's down 16, and it's a parabola. Well, where is this graph greater than 0? I keep on clicking the wrong thing. When is this equation greater than 0? Well, it turns out it's greater than 0 everywhere over here and everywhere over here. So this is one way to do the answer. Your domain for this problem is actually negative infinity to negative 4, union 4 to infinity. The other way to do it is this x squared minus 16 greater than 0. Notice that this is a quadratic. I can't solve it like I did the other two. The other two were linear, so I just moved terms around and got the x by itself. Here, I can get the x by itself, but it doesn't mean anything. What we do instead is if you have a quadratic or anything that's not linear, okay, so in this case a quadratic, what you're going to do is you're going to set it equal to 0. You're going to solve. Then you're going to make a number line. With your answers. So in this case, x squared minus 16 equals 0. This is just x minus 4, x plus 4 equals 0. X equals 4, x equals negative 4. Those aren't your answers because this is a nonlinear problem. It's a different type of problem. So whenever you have something that's not mx plus b, you create your number line. We put the tick marks on there. But now what we're going to do is we're going to plug a point in each region to see if it's positive or negative. Just like we did at the end of exam 3. So the points I'm going to pick are negative 6, 0, and 6. Why not? And the equation, remember, is x squared minus 16. So if I have negative 6 squared minus 16, the answer to that is 36 minus 16 is 20. Okay. 0 squared minus 16, that's negative 16. 6 squared minus 16 is also 20. And all I care about, though, is the sign. This is positive, this is negative, this is positive. And so all the answers that were positive, I keep. The answers that were negative, I throw out. So my domain is the same domain that I got earlier. It's negative infinity to negative 4, 4 to infinity. So those are the ways to do it if it's not linear. You can use the graphing approach. I didn't graph the log, I graphed the inside. The inside was x squared minus 16. I know what the graph of that looks like. And I'm looking for where it's greater than 0. Greater than 0 just means above the axis. Well, this parabola is above the axis everywhere to the left of negative 4 and everywhere to the right of 4. In the middle, it's below the axis, so I don't count it. So that's my answer. If you want to do it the algebra way, what you do is you set it equal to 0, get your answers, but then you have to pick a point in each region to see if it's positive or negative. And it's the same, you get the same result as before. On the homework, you have one of these, so I wanted to do this one. Most of the stuff we do in this section will be nice and happy. It'll be these linear problems. But every once in a while, you'll get one that's a little tougher, and you can't do it the same way. If it's not mx plus b, you have to solve it using this more complicated method. All right, almost done. Word problems, and that is it. Okay, so I'm going to save the last page for y'all to do on your own because word problems. But let's do these two problems here, and that'll be it. So the intensity of an earthquake is measured by a seismograph, a device that measures the amplitude of shock waves. Okay, so here's the formula that they're giving you. Okay, where IO equals a level 0 earthquake. It's used for reference. If you want to see what a level 0 earthquake is, just jump up and down. That's a level 0 earthquake. Okay, it's just very, 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 very slight vibrations. Okay, now because the magnitude of things increases rapidly, so when you have the Richter scale, usually a 0, and then you have a 1, and then you have a 2, a 3, and a 4, and so on. And so, remember, like I said, this one is just jump up and down. And that's a level 0 earthquake. Whereas a level 1 earthquake will probably be maybe the trash, the dump truck. Okay, so it's a big truck, and so usually you can hear it, and everything kind of shakes a little bit as it's coming because it's so huge. All right, a level 2 is something a lot more massive. This is probably like very harsh winds, lots of shaking. And then 3, this is where it starts to get really, really bad. This is where people can get hurt. And so on. So when it comes to earthquakes, though, we have this scale, and it tends to fool people because these are answers to this equation. But notice that this equation is a log. This means to get from one to the other, it's times 10. 10 times more powerful in order for the log to read to the next level. This thing too, times 10. Times 10. All right? Now, if you wanted to have a scale, then 9 This is the really huge ones that you see that, like the Japan earthquake or something. It affects the entire nation. And then you can keep on going, and then you get crazy stuff. Like, let's say if there was a 12, this would be what you would see in, like, a DBZ fight from anime. Like all the destruction and stuff, where they're like destroying planets and things, that would be like a degree 12 earthquake. Usually those, yeah, don't get that powerful. Usually earthquakes will range between 9, 10, um, and they'll kind of stay around there. But anyway, so determine the magnitude of the earthquake using the original estimate for intensity. So let's read the problem. I kind of got off track. The intensities of earthquakes are measured with seismographs all over the world. Suppose the intensity of a medium earthquake, originally reported as 10 raised to the 5.4 times the level 0 earthquake. Later, the values revised to 10 to the 5.8 times IO. Determine the magnitude of the earthquake that was originally estimated. So here they're saying that I, the intensity, the original intensity, sorry, not original, but the initial intensity that they measured was equal to 10 to the 5.4 times IO, a level 0 earthquake. So if I plug that in, that's just 10 raised to the 5.4 IO over IO. Notice the IOs cancel out. And you have log of 10 raised to the 5.4, which is a 5.4. So a 5.4 level earthquake was originally estimated. They do the math again, and they changed their value to 10 to the 5.8 IO. Again, the IOs cancel. And so we have log base 10 to the 5.8. The log and the 10 cancel out, and you're left with just 5.8. Pretty simple. But then here's the part that gets people. How many times more intense was the earthquake than originally thought? Well, the intensity isn't, this is just a reference level. Now, the actual intensity was 10 to the 5.8. That was the new one. And the old one was 10 to the 5.4. Now, if I divide the two, I'll get how many times more powerful the actual earthquake was than it was originally estimated. Sorry, let me make that. All right, a little bit smaller. So all you got to do is go to your calculator and type in 10 raised to the 5.8 divided by 10 raised to the 5.4. And so we get 2.52. Round to one decimal place, so 2.5. So this is what gets people, because they read the news and they say, oh, look, the earthquake that was 5.4 was really a 5.8. And when you look at it that way, that doesn't, oh, that's not that much, that's just 0.4. But in reality, it's a huge difference. What that means is that the earthquake was really 2.5 times more powerful than initially predicted. Imagine taking a test and you study for it, and then it ends up being 2.5 times harder than you thought it was. That's no fun. Anyway, here's another. You know what? I'll save this one for you to do on your own because it's pretty much exactly the same thing that we just did. This one, I think there's two problems. I'll do the first one, and I'll leave the other one for y'all. So another time that you'll see logs in real life is not just the Richter scale for earthquakes, but you also see them in the pH level for acidity and base. All right? So the formula is just this formula right here. It's a pretty happy formula. Negative log of H plus, and here's the sciencey definition of what it is. Okay, the pH scale ranges from 0 to 14. Pure water is neutral, so it's 7, whereas something that's extremely acidic would be 0, something extremely basic would be a 14. Okay, so vinegar and lemon juice are both acids. Their H plus values are, and now they give them this here, respectively. So find the pH for vinegar. So we're just going to use the formula. The pH is equal to negative log, and for vinegar is 5.0 times 10 to the negative 3. And so we're just going to work it out. Hold on. Just want to make sure I'm not doing anything silly. All right, sorry about that. I just had a little brain fart. So for this one, I'm just going to go ahead and type it in the calculator. I have negative log of 5. That's just 5 times 10 raised to the negative 3. And so we get 2.301. Okay, so that's for A. B, what's the pH for lemon juice? We do the same thing. This is 1. This one's easier. And so I can do this one in my head because the base 10 and there's a 10. But if you want to follow what we did earlier, you can just say negative log of 1 times 10 to the negative 2. 2. And there you go. So the pH for vinegar is 2.3. The pH for lemon juice is 2. So which one is more acidic? So here's lemon juice. Vinegar is right here. The more acidic it is, the closer it is to 0. So the lemon juice is more acidic. Right? Anyway, so if you have any questions over this assignment, just let me know. This was part C. But the next question is just the same. There's my dad joke. Meh. Basic. All right. Let me know if you have any questions. I'll post another video where I'll do the missing 2 word problems, and I'll also work out the parts that I skipped over here on the first try. All right, so y'all have a good one. Take care of yourselves. Be safe.